Hello, I hope you're able to see my screen and I'm audible. Can you please comment as soon as you're able to see this? Okay, amazing. So let's start with our session for today. Okay. Um, okay. The first thing here is why this webinar? Okay. Okay, before that, just a quick this thing. Can you just tell how many years of experience you have and from which country do you belong in the chat, just so that we have an idea of the amount of people with which experience that they have, so we can go in that much depth. Hmm. Okay. I see a lot of people replying. Yes. Oh wow. Okay. Okay. 13, 10, 2. Okay. 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 We have various engineers from different background. Oh, okay. Italy, Morocco, India, Kuwait. Okay, amazing, amazing, amazing. Okay, okay. So let's start with this webinar. Okay, so starting with this webinar, first is why is this webinar in the first place? Is what I believe here is that like a chef who has to prepare some kind of amazing food, he has some input ingredients available that he would use to make whatever recipe. But when an finished product is made, the real magic is with the chef. He used his brain to understand what was the thing, how do you mix components together, how do you optimize things to make that final product. Similar is what I feel is the role of an engineer. For example, an engineer gets a lot of input documents that we will soon see, and those documents an engineer has to understand of how do you extract data and how do you process that and how do you take an engineering decision. And that is the magic of the engineer, and that is what we will try to explore, at least the first part of it, in this webinar. And I hope in the coming webinars we will try to maybe explore more in depth, as in based on your comments which part you would want to be explored in depth. So starting with that, once we make all of this data come together, then you can make an engineering decision to select a particular control valve for a particular application. That being said, let us first start by understanding is, as a chef, you would have certain input ingredients required. So for making a data sheet also, you would require certain input documents, for example PNID, process data sheet, piping material specifications, and design basis. Once you have these things available, then it becomes easier for you to make your data sheet. So your first step in making the data sheet is to gather all of these input documents. If you don't have any of these, then the first step is to first have these documents, and the second thing is to verify them. A lot of time what happens is, especially in the process data, for example, you might get something which is too much over specified, or it comes from hydraulic calculations but it is not yet checked by the process engineer, especially when you will do control valve calculations. So for that case, the first thing in checking of or making a data sheet is that first you have to have accuracy of all of these documents. Once that is done, then you can move to prepare your amazing meal that is going to have a good final output. Okay. That being said, we'll try to divide the webinar into four sections. Okay. First is, okay, before that, what is your top query in control valves? What is the thing that you get stuck a lot? Can you put in the comments what do you think is your biggest problem when it comes to control valve? Let us see if we are able to address in this webinar, or maybe at the end of the webinar we can take those topics. Okay, I see. Selection, points to check in TBE. Okay, selection, choked flow, trim and selection of the types of trim which are available. Okay. If cavitation occurs, what will be the suggestion by engineer to rectify? Okay. Fugitive emission type testing. Ah, this seems to be from Mayank. Okay. Trim selection, overall designing material, how to select particular material. Okay, okay. Rangeability, controllability, choked flow. Okay, characteristic selection of CV. Okay, valve characteristics. Okay, good, good, good. Oh my God, we have a lot of questions. Okay, okay, makes sense. Okay. So, I hope this webinar should help you, and whatever parts you would want to describe or you want me to describe in depth, you can put it in the comments. I'll try my best, and then maybe we can even have a part two, seeing your amazing response on whatever are specific parts. Okay. So first 15 minutes we will focus on the valve body selection. That was going to be our first part. Then the next 15 minutes we'll focus on the trim selection, especially which type of trim to be selected, and we'll try to have some kind of thumb rules or kind of like an algorithm, so that when you make your data sheet you have a basic idea of, okay, fine, for this application this should usually be the trim type selection. Then next we will look at material selection. Again, these 4 points I have come across by your questions only over the years, at least for the past 8 years. Whenever I have seen, these were usually the 4 questions, and the final one was control valve standards also. At least, and you should have an overview, not in depth, but at least you should know the basic international standards that are applicable when it comes to control valves. Okay, so let's begin. First is the selection process. So when it comes to selection, uh, what do you think is the parameter that comes to your mind? How do you select a valve? Is there any specific guideline that you follow, or you just go by the PNID? Whatever is written there is what you would follow. How do you usually go with selecting? Let us see in the chat what people have to say. Okay, okay, good. Okay. Okay, there's a lot of confusion seems to be on the selection part of it. Okay, design basis makes sense. Okay, okay. You okay? Types. Okay, whatever is client specifications. Okay, okay. Based on surveys, based on process feed. Okay, CVN process parameters. Okay, process requirement. Okay, okay. Flow, pressure, temperature. Okay, specifications. Okay, 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 makes sense. So now here what I suggest is, as an engineer we should also add value. Whenever we get certain specifications, they are usually based on certain I would say is experience of the client, or maybe based on certain licensor requirement. However, those are not rules set on stone. So if as an engineer you find out that those things don't make sense, or for example you can have an optimum solution for that case, I think it is definitely a good choice to select a valve accordingly. And sometimes the PNIDs and specifications sometimes make an error. So as an engineer, it is very important for you to catch those. So let us first start with understanding the valve body selection as a first case. So I would start here by explaining is basically, if you want to protect yourself, and should you use a mosquito repellent or should you use a machine gun, for example. Now, this question sounds ridiculous, but if you actually look, the answer is not clear. It depends on what is in front of you. If it's just a cockroach, the mosquito repellent or the cockroach repellent would be very good for you. But a machine gun, even though is better, but it's over specified. So the first thing in the valve selection, which some of you said in the comments, is basically to understand the exact application. Once you know the application, we will go into details of what in the application you should know. But the point is, first you should know the application. Where do you want to apply the valve? And that is where we go forward. For example, if you have a dinosaur, for example, your mosquito repellent would definitely not be, sufficient for that case. In that case, you definitely need a machine gun, even though it is costly. So you should know the cost difference between various kind of valves, but that is not the only criteria to select. First is you need to know what you're dealing with, and then you can select based on your application that for example, how can you be cost effective plus technically compatible at the same time. Okay, that being the case, let us look as to how to understand a particular application. So now when we go here, the first thing we need to understand is the application requiring precise flow control or not? Let me give you an example. For example, let's say you have a utility service. Now, utility service, you don't require it to be completely precise. It can be, I would say nearly precise, but you don't need it to be exactly precise. However, if you are exporting or if you are having petroleum products, or for example it's a paint line where you need to mix in a certain proportion, there your precise flow becomes very important. In that case, you have to first know is how is your application, does it require very precise flow or not. Second thing is differential pressure. Okay, one of my friends in Shell, he told me one thing to remember. If you want to do control valves, differential pressure or the pressure drop across the valve is going to be your number one characteristic that will help you to understand which valve, which trim, in control valve sizing, in selecting the correct CV. For everything, your DP becomes extremely important. So this is what we have to pay very attention. How much is the differential pressure? It is less, for example 5 bar, 2 bar, or if it is 50 bar, 100 bar of pressure. So as the pressure changes, your selection has to definitely reflect that. Third thing is what I call as CFC and issues. We will deal with that as we come there. And finally is your budget, a least in the list, but according to clients and your end users, definitely that is one of the most important thing to them. But as an engineer, I put that at the last. First is because to understand that if it follows the first three criteria, only then can you look for budget. If your valve cannot cater to application, it doesn't make sense even if your valve is the most cheapest. Then you have some smaller parameters also, like the leakage requirement, line size, and other, I think around 20 parameters, but these four have usually been the strong parameters while deciding any application. Okay, now first let us look into the cost effective pattern. Okay, now when you get to cost effective pattern, what I would suggest is, uh, there are a lot of valves available with us, but with respect to their design, not all of them are good for control. So let us ignore as of right now is gate valves and the common ball valves. We'll keep segmented ball valves, plug valves with us, plus we'll keep is globe valves and butterfly valves, because these are usually the four types which are usually used for control applications. For special applications you have diaphragm seals, diaphragm type valves, etc., but those are very, very high viscous applications and very specific industry related stuff. So let us first discuss this overall as a graph. Now when it comes to your application, you have butterfly, segmented ball and globe. Now here, which is the most cost effective option? Can you put it in the comments which you think is the most cost effective option for you? Okay, okay, let's check. Selection as per text. Okay, application. I see, I see. Okay, somebody says globe is the cheapest, butterfly is the cheapest. Okay, okay, globe, butterfly, depends on application. Okay, safe answer. Globe valves, butterfly valves, butterfly. Okay, okay, depends on size. Okay, very good point. Okay, very good. Ball valve, okay, segmented. Okay, 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 makes sense, makes sense, depends on size. Okay, okay, okay. So good, I think people have a very good decent understanding. Okay, so when we go forward here, ideally speaking, in a very broader picture, butterfly valves are usually the most cheapest. Then comes your segmented ball and plug valves, and then comes your globe valves. If you see logically, also a butterfly valve is a very thin valve with completely, the material itself used to make it is less. Then comes your segmented ball or plug valves, and then if you see the globe valve design with respect to its complex flow path, it is very difficult to manufacture it very cheaply. So comparatively, if you see butterfly, we can keep as of now as segmented ball and plug and then the globe valve. But then one more person gave a very important answer in comment. Okay, before that, I would say maybe you can imagine the butterfly valve just for our understanding, kind of like the cockroach. So wherever the application is simple, as an engineer, your first chance is to see whether can you have butterfly valve implemented there. If that doesn't work out, then you look for whether segmented plug can work or globe can work. Okay. That being said, now let's look into the second important point, which is size. Okay, now the budget will greatly depend on your line size. So as somebody said in the comments very clearly, as the line sizes increases, the impact of the size on globe valve will become 2 times, 4 times. It will increase dramatically as your line sizes increases, and also the maintenance will become tougher. So in that case, if your line size is very large, first look, can you make butterfly valve fit in your application? If not, then look for segmented ball or plug valve design. And if nothing works out, then maybe you can look for a globe valve design, or you should consult a specialist if the line size is too big. Because globe valve maintaining at such high line sizes and with such a huge pressure drop is something tricky. Okay. That being said, the second application or the point which we discussed was precise flow. Now, when it comes to precise flow, we have globe, segmented ball, plug, butterfly. Can you tell me which one has the most precise flow control capability available with them? Which one could have the most precise flow? Let's look at the comment section. Okay. Okay. Oh my God. Okay. 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 At our industries. Okay. Okay. I'll also talk about based on your industry, which is usually preferred. Okay. Okay. Globe definitely. Globe valve. Globe valve. Globe valve. Globe. Okay. 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 I think this point is very clear with almost everybody. So let us go quickly on this point. Globe has definitely the winner. You go to any control valve, whether you go to manufacturer, you read any reference book, any standard, Globe valve definitely wins here. They have very precise control. So if you are having some petroleum products, etc., definitely you should first go for Globe valve regardless of the cost if you want precise flow control especially. Okay. Now, the most critical application here is CFCN. What I call CFCN is cavitation, flashing, choked flow, and noise. For these four issues, which is usually what a control valve mostly faces, here the valve selection again becomes important. If you have any of these four criterias, then which valve is better for you? Overall speaking, in terms of the solutions for such cases, if you see, the CFCN is basically also having a relation to differential pressure. What I mean by that is, if you would look into your control valve sizing, or if you have already done, you would notice that the applications which have higher DP, which have challenging DP values, would mostly be experiencing these CFCN issues, which is cavitation, flashing, choked flow, noise, etc. So I would see kind of they are interrelated to each other. So for applications which have high differential pressure, or you have already experienced CFCN happening through your calculation, for those applications, which valves should you choose? The answer has to be, out of the three, it is definitely going to be globe valves. Why is that the case? Is because globe valves, first of all, they have a lot of options. For example, if you want low noise trim, for you want to have different kind of characteristics, it becomes easier when it comes to and handling. If you see a butterfly valve, in terms of its construction, it's basically a vane which is rotating. So now imagine at especially, I would say, 60 or 70, 80 degrees, that is when at that time, to maintain its state at a very high DP, let's imagine 100 bar of DP, it's too difficult, it will start to vibrate here. So it's very difficult. You have certain valves which have come in the market, which are called as triple offset butterfly valves, but still it is very tricky to maintain that kind of position in such high differential pressures. So for that case, I would definitely suggest is that you should definitely go for globe valves as long as it is possible, and then you can have in the middle, which is your segmented ball or plug valves to be used in case if you can cater to those applications. Okay, now getting to industries, can you tell me generally for oil and gas, which is the most common type of valve used? For pulp and paper and for wastewater, generally the case. Let's see what is your response. Okay. Okay. For wastewater, what would be the valve? For wastewater? Okay, okay. People seem to be from oil and gas more here. Okay, okay. Perfect, perfect, perfect. Okay. Wastewater. Okay. Yes, yes. Perfect, perfect, perfect. Okay, makes sense. So, okay, we have some chemical background. Okay, fine. Yes, yes, yes. Perfect. Okay. So, okay. So now based on what we learned, if you also apply it to industries, you will generally see that for oil and gas, which majority of you have answered and seen in your books, is that the traditional sector preference is globe. Now, when I say globe for oil and gas, does not mean that it should be globe for any XYZ project, XYZ line. It should definitely depend. In oil and gas, also you have utility section where you will have water transporting. So there, if you see a globe valve, you can definitely try to replace that with a butterfly valve and save cost and maybe have a value addition as an engineer in the project. So but overall speaking, because oil and gas projects are generally more challenging in terms of their differential pressures that you will face, for example, a ethane cracker. So all those projects generally you would see that all engineers usually recommend a globe valve. When it comes to pulp and paper, it is not extremely challenging but not that easy as just water treatment plants. So generally they have a generally they have a preference for segmented ball or plug valve design. And finally, when it gets to wastewater, most of you answered because those are not challenging applications, you might first try to go for a butterfly valve. So this is how whenever you see any PNID, you at least have a basic understanding of which type of valve should you select based on that application. So what we learned was four important things which comes on is first is the budget, that highly depends on the size of the valve. Then it depends is which type of application you have, for example high differential pressures or do you have CFCN issues happening. And finally you would also have to see is how much precise your flow control is to be required. So we'll make a quick I would say a summary. So first, as an engineer, when you're looking, you will see do you have these three issues there: CFCN, high differential pressure, or precise flow control. If that is the case, the answer is yes. Then you should look for globe valve, which is your most costliest option, but you have no choice as an engineer. If no, then you can look for some budget friendly options. For example, you will first try for butterfly valve. If butterfly doesn't work, then maybe you can look for some more tough applications, for example segmented ball plug valve, which can be in the middle. So basically you have is the best is the globe in terms of the overall applications, but the most costliest one. In the center you have is ball or segmented plug valve, and finally you have is the butterfly valve, which is the most cost effective option. This is an overall thumb rule that I would like to share with you. And if you have any other suggestions, please put it in the comments. I'll definitely look into them. Okay, now let's move on to the second part of it, which is trim type selection. Now, this is definitely very confusing when it gets to especially globe valves. And I've got a lot of queries when it comes to trim type selection, especially when it comes to globe valve applications. So when you get to trim for globe valve, you have plug guided trim, you have balanced type, unbalanced type, cage guided, trim guided, single port, double port. Then you have characteristics like linear, quick opening, equal percentage. So now with all of these different types, it becomes very confusing how to mix and match them together based on a particular application. So now for trim type selection, first I would like to make it at least divided into subcategories, and then we will explore them. So the first category which I call is unbalanced and a balanced trim design. Then the second opposite side on the spectrum is basically where you have linear characteristics, quick opening and equal percentage. Then you have something called as cage guided design and plug guided trim. And then finally you have is dual port and single port globe valves available. Now, can you tell me in comments which are usually the trim type that you have used in your projects? Okay, And I see some amazing questions also asked, so I'll also answer them hopefully if we get time at the end of the session. Okay, cage guided, linear, okay, equal percentage. In our plants, it's under mechanical scope. Oh my god, okay. Equal percentage, not yet done. Okay, no problem, no problem. Equal percentage, balanced trim design. See, now you get combinations coming in. Okay, equal percentage, unbalanced trim. Equal percentage, plug guided, balanced trim. All depends on application. Okay, Ashish, you've given giving answers for all as yes. All depends on applications. Okay, okay, very safe answer. Okay, okay, modified equal percentage. Oh wow. Cage guided in case of cavitation. Okay. Unbalanced equal percentage. Okay. Can you just add one more point is okay. Okay, okay, flow direction. Okay, okay, this is a good point. Okay. Single port most generally I used. Okay, okay, balanced trim, unbalanced trim. Okay, 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 makes sense, makes sense. Okay, amazing. So I see is almost everybody has used some or the other configurations available. Okay, 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 makes sense. And I see is okay, and some things are quite common in between people. Okay, 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 some concepts. For example, the equal percentages I see a lot of times coming in. Okay, okay. So why are those things happening? Let us also look into that. And what we'll do is we'll try to have a flow chart. So, and what I'll do is at the end of the presentation, I'll share with you this PPT as well, so you can have that flow chart. So whenever you are doing trim, you can maybe go through that flow chart with yes no, and then at least you have an overall idea which one you should select. So hopefully that makes things more valuable to you. Okay, getting to that, first thing is I want to explain this concept of how these so many these trims come into picture with something related to civil engineering. Now in civil engineering you have something called as cantilever. Now cantilever is basically a very simple design. If you see, cantilever means a support which is given by civil department, which is fixed at one end and the other end is unsupported. So basically if you want, you remember, I don't know if you have instrumentation trays which have to be laid, civil gives you this kind of support. So one side it is usually fixed and the other side is usually, because the trays are not very heavy, so they can easily rely on the beam that is given. Now that being the case, how does this basically help in our trim design? Let us look into that point. If you see here, this design is kind of similar if you see to a valve connected to a plug. If you see here, the top side is basically the fixed end that we have, and the bottom is something which is free, which is the unsupported end that we have. Okay, now what happens here is, if you see for any valve application, for example here, this is how your fluid is flowing through the valve. So this end is your fixed end and this end is your unsupported end. I hope this concept is now clear of how it relates first to civil department, and then we will understand what is the issue with this design. Now when you look here at this design, you can see that because it is supported at one end, the other end, if there is huge amount of I would say turbulence, or for example very high dp, it is very difficult to keep the other end stable. It will start to kind of oscillate, and this is especially not good for a valve which needs to have precise flow control. And that is why engineers were thinking a lot and were very confused as to how do you tackle this issue especially. And that is how came your dual ported design. Now what happens here is, in the dual ported design, if you see here as the way it is moving, it is supported at the fixed end which is from the actuator side, and at the bottom also it is supported. So how this was helping was, if you have very high dp, uh, this is just I'm giving you a example, maybe 30 bar, 50 bar, it depends on your application. We will look in the end as to when do you select dual ported design, but just giving an example, if the dp is high, then your plug is definitely going to oscillate a bit. So it is better from single port to go to a dual ported design. Okay. Now the other query that I have here is that once you have this design fixed, the fixed end is there, you would see in majority of the chat, very few people said dual ported design. If this design can cater for high DP, and most of you have your experiences in challenging applications, why didn't you select a dual ported design compared to a single port design? Can you give an answer why don't you select dual ported design in your projects? Is there any specific reason for that? Very good. Amazing. Amazing. So a lot of you have done a lot of research. Okay, you can't achieve have leakage classes. Okay, good. Good. Tight shut off. Okay. More leakage path. High leakage. Higher cost. Good point. Good point. Very good. Passing issue. Okay. If tight shutoff is not required, we can go for single port. Okay, no, but then what if your DP is very high and if you go with single port? Okay, valve size will increase, makes sense. Response time to tackle DP rapidly, difficult to maintain. Okay, good point. Not experienced in engineering. Yeah, it's okay, no problem. Yeah, definitely. Okay, okay, but I see a lot of amazing points here. Okay, okay. So basically with dual ported design, as some of you said, there is going to be an issue. So but overall, remember one thing: when it comes to dual port and single port valve plug guided is good for low differential pressure applications. Dual port is good for high differential pressure applications. Okay, then now let's look into answering the question why it is not used in most of the applications. The first important thing is leakage paths are increased. You have one point of contact with the fluid. There, if the shutoff is not good, you will have some fluid leaking. If you have two ports, definitely it's going to have four paths of leakage available. Second is higher cost, because the body size is going to definitely increase, which also some of you said in the comments. That will definitely make it, not a good choice, especially for your clients. And then you have the third thing is they are heavier. Because of the two ported design, they make it far heavier valves compared to your regular application. Then this bigger design also has to be accommodated. Again, that becomes difficult for the size to be available in the plant, the clearance is available to remove the valve out, etc. So all of these factors were actually having an issue, and up till 1960s engineers had no solution. So it was very clear for them at that point of time, if it's less DP, low DP applications, I go for a single port valve. If it's heavier or high DP applications, I will go for a dual ported design. That was it. But then what happened here is, what I would like to share is the idea of cage guided came into picture. Now what happens with cage guided is, we will get to the characteristics of trim, but before that what I wanted to explain was that cage guided, why did the need come for cage guided? If you see here, a lot of people also said in high DP I use cage guided valves. You are correct. What happens here is, in cage guided design is the top end is anyways fixed, basically with some kind of support. The bottom here is also fixed because the cage will never move, it is the plug that moves inside the cage. So now you have better stability at high differential pressure applications, and this reduces the idea of leakage path. This reduces the idea of having a bigger design or two ports available. Also the space requirements have reduced, so this seems to make a lot of sense. However, there is a big however. If your service has big solid particles which could get plugged into your cage, then maybe you need to still think about dual ported design. They are not traditionally used. Most applications you should avoid them. If nothing works out and if you know your fluid is that much tricky, then maybe you might need to go for a dual ported design. Otherwise, if it's high DP, you should go for a cage guided design is a better choice. Okay. Now, once we get into that, now what I want to share with you is the balanced and the unbalanced trim design, and then we will, club all of these trims together and try to make a, kind of like an algorithm. So now here, when I'm trying to talk about balanced or unbalanced design, if you see here, this is the plug, this is the seat assembly available, and this is the fluid forces which are hitting to it. Now, what is going to happen is the fluid forces, let us call it as P2, and the actuator force is P1. This is very basic, but I still want, because I saw there are engineers with 1 year of experience or GTs. So, let us include them also in our conversation. So first, try to get to basics, and then we will look into more advanced, and I'll try to answer more advanced queries also as you get along. Okay, so now P1 and P2, if I want the valve to be closed, P1 has to be greater than P2, which makes sense, right? If actuator force is greater, it is going to close and not allow the fluid to enter. Here, as some of you said in the comments, this means the actuator has to put all the power. Now when you go for a balanced trim design, if you see there is this small hole here, what does this small hole do over here is, at this particular portion, is that once you have that hole available, the fluid forces can enter through the hole and go to the opposite side. Once they go to the opposite side, the actuator and the fluid forces become friends with each other, and it's kind of like they'll further support and allow the force to add up. So for example, the fluid force was P2, and on the other side you have actuator force P1 plus P2 acting from the opposite direction. So this greatly reduces your load on the actuator. When is this design good? It is good when you have very high DP or your line size is too large, because if your line size is too large, your actuator sizing will become again big. So either if your DP is too high, so even if the line size is small but the DP is extremely high, you should still go for a balanced trim design. Why? Because it will save a lot of your cost in terms of the actuator sizing. But again, there is a big but. The reason is, if your fluid even has smaller solid particles, still they'll get stuck in your hole, basically the balancing hole, and your actuator will not be able to function well because it is not designed for that high pressure. Now why am I telling you this? Is a lot of times what happens as engineers is, you give a requisition for a particular vendor, the vendor will definitely has to save cost. He would not see any clause maintained in your data sheet saying that there is going to be some solid particles. You missed to mention that clause, and he gives you a balanced design. Now when it gets to plant, your valve will actually, that hole will get stuck and your valve will not function properly. It will not close and you will have extremely high leakage rate. First thing. Second thing is, if you can see my mouse here, once the fluid enters here at this particular point, again there's going to be another leakage path available. So your leakage chances also increases. So again you need to be very cautious that, are you okay to have slight amount of leakage available here? Okay. Now this gets me to a very important question, that is about leakage rates. I want to maybe mention a small point. I don't know if, let's see, um, which leakage class is usually specified in your data sheets? Which is the most stringent one that you usually use? Okay, one person has mentioned, uh, in chlorine application we can't use balance stream. Yes, makes sense. Yes, okay, okay. Class 4, class 6, class 4. Okay, okay. It is usually the class 4, class 6. Okay, okay, okay. Now here I would, okay, okay, and CFC. Yes, yes, yes. Okay. Class 6 for, no, on off valves we don't use this standard class 6. On off valves we have rate AB. Okay, no, okay, okay. 4 6. Okay, on off valve is a different topic, we will deal separately, maybe at a separate webinar. Okay, okay, very good point. I heard 6 for tight shut off. Okay, this is what I wanted to get to it. you know uh, why am I saying about this trim is, lot of times the client or the end user sometimes rejects, for example, that I don't want a balanced trim design because my leakage rate will increase. I need example an X amount, let's say a tight shut off, which is, or some people say it as class 6 for example. Okay, now my first question here is, if you read the ANSI FCI standard, the first thing you will notice is that whatever leakage class that is mentioned as class 6 with bubble shut off and only a few bubbles are visible, I don't want to go in depth, but basically I want to make you aware that that is only at standard conditions, at a very small pressure drop, temperature, fluid, etc. What I mean to say by that is, if your application requires extremely tight shutoff, do not use a control valve. Recommend to your client also, or your original OEM, whoever is the person, that please understand that a control valve, its inherent capacity is to control, not to shut off. Even if you take a class 6 shut off, it will definitely not have the capabilities to actually shut off still, because at higher dp, for example 30-50 bar, your valve is definitely going to leak. So what I suggest as a solution in that case is, it is costly, but if you need very high shut off, then what you should do is have a control valve, and at the downstream have a actual on off valve. Ball valves for example, or gate valves for example, have very good shut off capabilities, and they are predictable. Once you shut off, you definitely know that it is going to be shut off. I am not saying this for any personal gain, but accidents have happened, for example, in Husky refinery, where if you remember, the control valve got eroded. Okay, the second thing is, because control valve is continuously in application, the trims get eroded. So there was that slight leak in the control valve. So when the equipment was removed, slight air passed into it, which got together with hydrocarbon, and you know what happens where air gets in contact with hydrocarbon. So what I mean to say as engineers is, if you see an application requires very tight shut off, try to recommend for a control valve for control application, and for shut off recommend a separate on off valve is a better choice. So for this cases, if client rejects, oh I need extremely tight shut off, don't use a balanced trim, question him, how much tight shut off do you need, how critical is the application, will it cause a lot of lives to be lost? If yes, then I think we can spend easily on having another valve to do the shut off application. Okay, that being said, now let us look into the trim selection chart. So first you have to see, which I told you initially, a friend of mine has always been an advocate of DP. So if the DP is high or not, DP is like 1 2 bar is like very minimum. As the DP increases 50 bar, 100 bar, you have to understand how is the DP. Once you know that, then you look for, is the line size large. If the line size is also not large, then you should go for a single port plug guided means the plug itself is contoured to that level instead of cage guided. You might go with plug guided, should be okay for very small size, the dp is also less, go for that, save your cost. If that is not possible, if your dp is very high, then you see whether the service is clean or not. Because if your service is dirty service, even if you have something like unbalanced trim or cage guided, then you have to look how dirty is the service. If your service is clean, the answer is yes, and your line size is also large, then you should prefer to go with a balanced trim design with a cage guided design. So inside the cage guided with a balanced trim is your best choice to go. If that is not the case, and if your service is extremely dirty, it has very hard and strong particles which are there, in that case maybe you might have to go for a dual ported valve, so that the valve stays in its position at very high dps, and it has a lot of dirty fluids, it still should be able to handle it. But this side can be discussed with your valve vendor, and you people can come together and find if there is some other solution. If not, then maybe you might have to go for a dual ported design. Now in this algorithm, what we have yet not considered is the characteristics, whether it's going to be linear, equal percentage, or quick opening. So now let's look at only that part. Here what I would suggest in those characteristic opening is, I would maybe give you a golf example to make that point. Is example, if you see here, I need to reach to point A1, which is the winning point, okay? And you have B1 and C1, two different points for hitting the golf ball. Whenever I hit a ball to reach to A1, there is wind which acts and causes my ball to fall in B1. So now what is an engineer's mind here? You can't control the wind, but you can definitely control your stroke and your ability. So what do is you aim for C1. So you know that as soon as I aim for C1, eventually the wind is going to come, which is a uncertain factor, but to kind of extent you can manipulate. Okay, fine, okay, it causes your valve or your basically ball to move 10 centimeters behind, and then you get to A1. So basically you try to understand how the non-linearities of wind works, and then eventually you get to your point. This is the same concept when it comes to your valve characteristics. If you see a lot of okay there's a lot of different literature available when it comes to your characteristic selections. A lot of people have their different opinions. I respect all of them. This is what I personally find it to be valuable and what I usually use. I'm sharing it with you, and I will also explain the concept. Then it is on to you to decide of how you want to select your characteristics. The first thing if you see here is they mention something called as del p max by del p min, which is under the ratio of 2 is to 1 or higher. So the overall concept is very simple. The concept is that if you have variations in the dB, ideally you are expecting your valve to be linear. Everybody wants the valve to be linear, but because you can't control the dPs in the plant because they are continuously fluctuating, if the dP variation is high, which you see on the right hand side here, the percentage selection should be usually be equal percentage there. If your dP variation is less in and of itself, you should usually go for linear. However, there are certain people who recommend certain type of characteristics based on application. We will also look into that point. So for trim characteristic selection, I would say, is the dP fluctuating? Is it greater than 2 is to 1? Is it fluctuating? No. Then go for linear characteristics is usually recommended. Then if your dP fluctuation is higher, you should go for equal characteristics. Most of you people who are working, you might have selected equal percentage characteristics. Sometimes it is just because you found in some other data sheet and you copy and pasted the same data, which is not correct. But most applications are tricky for us. But when it gets to applications, we can also have this thumb rule that usually level applications are kind of simple. So usually you might see linear mentioned more there most of the times. When it comes to flow or pressure applications, these are kind of fluctuating a lot. So usually you will have equal characteristics trim mentioned here. But I would say go with this rule of 2 is to 1 and 5 is to 1. Less dP fluctuation, go with linear. High dP fluctuation, go with equal percentage. Now here one point, what if you mention an incorrect characteristics and you get to plant? Once that happens, know that these characteristics first, because of the latest positioners which have come in the market, you can still modify it if they are configured correctly. So in that case, if your characteristic selection is not that accurate, you can still find a solution out. However, relying on the positioner to make your characteristics is not a good option. Try to keep your plug and your cage designed in the correct characteristics. That should be hopefully more helpful to you. And if you have cage guided, you can remove one cage and put another cage also. Still not recommended. First thing is design the right valve from the initial position. Better is not to make any changes at site, is what I personally prefer. Okay, third important thing is material selection. I have got a lot of questions from engineers asking about material selections. Can you quickly put on the chat what is your material selection strategy? How do you select a particular material for a valve? Okay, I see a question. Okay, okay, based on process fluid. Okay, based on process fluid, one class higher than pipe. Okay, you meant okay, okay. Based on the liquid in the line, based on medium, process medium. Okay. One higher than what piping has taken. Project piping specs. Okay. Based on temperature, based on PMS. Okay. Existing valve. But it's for manual valves. Okay. PMS. Okay. 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 So most people seem to be having. Okay. Based on pressure and temperature. Okay. I see. Okay. Liquid suitable material. Yes. Yes. Makes sense. Okay. 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 Beautiful. Beautiful. Okay. 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 So now here, first, what I would want to share with you is when I look at those slides, uh, first thing is I would agree, yes, PMS is definitely important, but as an engineer, you need to know the basics of the materials. Okay. Now the first thing is, before I start with selection, um, first thing is in terms of material selection, the standard itself becomes confusing to read the materials. Like for example, when I had engineers with me, the first thing was they were confused in terms of how our materials named. And maybe we have some young engineers also. So I'll just give you a quick understanding of the name of the materials. So for example, first, before we select is to know how the materials are actually named in their way. So for example, when you see UNS numbering system, you see something like this mentioned here, where this is your main material and this is your subgrade. Now this subgrade will vary. For example, 316L you have 03 written in the end. So some vendors give you materials mentioned in this format. Sometimes you might have something in the ASTM format. Here you would have is like this grade, which is the let's not answer first. You have these two grades available here, which is actually nothing but 316. One is the forged grade and one is the cast grade. The forged grade is something which you beat up and then you make it. Cast is where you cast it into a mold, it gets cold, and then that's how you get the material. Now why is ASTM done this is because you have more grades also with ASTM, but the reason is that forged grades are generally considered to be very hard compared to the cast version. As an engineer, why I stressed this point is I would not name, but after talking to few vendors, there are certain companies for a certain valve material, they want it to be forged. So if the vendor has given the cast version of that valve, the valve body, it was rejected, and at a very later stage. So the vendors be very cautious. If the vendor gives you UNS numbering system of the material, you don't know whether it is a cast grade or it's going to be a forged grade. And there are certain, I'm talking about world renowned companies that could reject by saying that no, they want the forged grade, and that is what is specified in their specifications. So be very cautious of this point as well, and that is the reason why I put this here. So both of these stand for nothing but 316, but are different grades. Okay. That being said, the DIN is another numbering system which is kind of like more confusing. Oh, 1.4401 has nothing to do with like 316 mentioned anywhere near to it, but it is the 316 grade, and in the end, if it ends with 04, it's 316L. So again, in this, you don't know whether it is forged or cast. So first thing is you should know if your application is requiring which kind of material. And I would like to give you some thumb rule. If your line size is small, vendors can give you forged version. If your line sizes are too huge, they it is difficult for them to give you forged version. If it is still mentioned in your spec that they want a forged version, then you should definitely raise this, and come ask them that you should give a, I would say, leniency here when it comes to very large sizes. Okay. That being said, now in terms of materials, as you said, it depends on particular service. I would also like to add like a chef who puts material or basically his spices to make a particular food. You need to know at least the basic components and how do they fit in when it comes to your application. So you have chilies, you have pepper, you have something. If you want to make something spicy, you will add more chilies into it. If you want to make something sweet, you would add sugar into it. So my point here is that the higher the quantity of something, the final output changes. Okay, I just wanted to ask one request. It might take for us maybe 20 minutes or 15 minutes more. Is it okay if we continue? I I wanted to teach you. It takes almost 20 25 hours to learn control valves, the entire thing. Uh, I'm so sorry. I wanted to complete within an hour, but this is just too much to complete. Okay. Oh wow, wow. Thank you so much for your respect. Yes, thank you so much. Okay, okay. I'll try to complete it. If something, oh wow, please continue for one more hour. Okay, sure. Thank you so much. We will try to complete as much. If not, I think we can have a part two of the session also. But I would not want to hurry up, just so that just to dump everything. If it takes time, definitely. But okay, thank you so much. We'll try to extend just for 15 minutes. Okay, okay. Thank you so much. Thank you so much. Okay, so now as you go here, I would similarly say, like how you make a dish, you should have these elements known to you. What is carbon, chromium, nickel, and then you can easily make a differentiation. Let me give you an example. I remember there was one engineer who was making a data sheet of control valves, and he said that the pipe material is mentioned as something written as 13% chromium. Okay. Now, his question is, should I use SS316 or not? See, the basic logic of selecting material, of how instrumentation engineers came up with the idea is, the pipe has certain fluid. The Already there are certain manual valves put, for example, or you have certain pipe material. So the pipe material has to definitely cater for that liquid service. So you can basically use the same material for your application, but it is not very easy. That is why some people mentioned in the chat that you go one level higher. I don't recommend it for all the valves because you will make your project very costly. If you have carbon steel and you always select SS316 for all your valve bodies, I don't know, but your project cost will definitely increase. So it should be based on a slight more deeper understanding. When it gets to small material, like for example diaphragm seal or a normal pressure transmitter, the material is very less. So you can go definitely a grade higher. So if it is going to be carbon steel, definitely choose stainless steel. It gets to valve, it has to be a bit more thought and in-depth understanding. So for that is the reason I'm trying to understand first the materials, as how do you, when you mix something in a food, how its taste changes. Similarly, when you mix something in a material, its composition is going to change. Now getting to your question, that if the pipe material is mentioned something like 13% chromium Cr, can I select SS316? I would want to answer this after we get maybe to the end of this part. Okay, so the first thing here is, I would compare chilies to be like carbon. You know, the more you provide, the more hotter the food gets. Similarly, carbon makes the material harder. The more you provide carbon, the more the material becomes harder. That means if I want to have an so that is why you would see a lot of pipes of piping are made of carbon steel, especially. Okay. One thing is, as these things become harder, they'll also become brittle at the same time. Example is glass. Glass is hard, but if I break it, it's very easy. It's brittle. So I can't keep adding carbon all the time. Similar to chilies, I can't keep adding chilies to make the food spicy. At a point of time, it becomes unbearable. Second thing is, why is this carbon thing important for you to know is, if you imagine carbon steel line and if you have SS316 valve body, so you might be more corrosion resistant than that. But if you go to your flange ratings, they will be inferior because they are not as hard, because carbon steel is harder. So maybe you might have to up your ratings. So that is how you should have an in-depth understanding that okay, I don't have carbon in my valve, so my body rating and the flange rating will be higher to match that of carbon. But corrosion resistant wise, I am better than carbon. SS316 is better. Why it is better, also we will get into that. But so remember, carbon is what personally I remember it as the chili. Use it as much as you want, but at a point of time, if it becomes too much carbon, it's going to make your very your material to be very hard. The second one which comes in as sprinklers is going to be chromium. Very important. The higher the chromium, the higher the ability to prevent corrosion. So when you have any carbon steel pipe and a stainless steel pipe, almost every one of you will answer that carbon steel pipe compared to SS316, the 316 will have higher corrosion resistance. Very simple. The reason is because we have put chromium into it. Now, now let's answer that question. So if the piping has 13% chromium is the pipe material, as an engineer, if you select SS316, the chromium percentage, it is very easy. You can check it online also, and you have the standard ASTM standard also has it very clearly defined how much percentage of chromium is required. It is 18%. So you are higher in the chromium side. So you should hopefully be good with the fluid. You are more corrosion resistant. However, be very cautious of the rating. Could be that your rating might be inferior, and you might, for example, from 300 flange rating, you might require it to be 600 flange rating or 900 flange rating, depending on that. However, fluid wise, you are good to go. Okay. Next component which comes in into our thing is going to be nickel. Now nickel, what it does is it adds stability at high temperature. Let me give you an example. Um, let's take for example Marsenic stainless steel for example. So if you see for steel also, it is divided into 410, 316, 316L, which is again lower carbon. So as you divide into materials, any material which has nickel more will have the ability to sustain high temperature, and as it reduces that, the ability to sustain high temperature will reduce. That being said, if you see in SS316, which if I ask you right now in the chat as well, you will say most applications, especially for instrumentation, you would see SS316. The reason is it has nickel, it has chromium, it has carbon. So it is comparatively hard, it has good corrosion resistance, and because of nickel it has stability at high temperature. So for most applications you will see SS316 being good, but that does not mean every single application. If your fluid is okay, if the piping material is carbon steel, if you don't need any high, especially high temperatures are not there, corrosion is not going to be there, then I prefer go with the carbon steel body. You will save a lot of cost. So based on that, you can select your application. Okay, one more thing I want to add up here is, whenever you look for, this is for a bit experienced engineers, whenever you look for piping material specifications, you always see something called as corrosion allowance. If you select your valve material same as the pipe material, which is carbon steel, then what you need to be cautious also is that the line material also has, or the pipe material also has a bit allowance for corrosion, because pipes are going to be for kilometers also, so you can't always have superior metals. So what they do is they increase the thickness a bit, that let the pipe corroded. So there's something called as corrosion rate per year. So the corrosion allowance is for example 6 mm or 10 mm. So that much area can get corroded and still the pipe is going to work well. If that is the case, and if the corrosion allowance limit is high, then remember, if your valve body is also of the same material, then I think it's a risky engineering decision. If the corrosion allowance is low, yes, you can go ahead with the same material, because our standards don't have, like the API standards don't have any specific clause, or at least I have not come across any clause which talks about corrosion allowance in our walls. So whatever is the thickness we assume. In that case, I would tell you is that please be very cautious if the corrosion allowance is high. Okay, that being said, another important thing is the trim material. According to me, do not be stingy on the trim material. Select the best, because the trim is going to experience highest amount of velocity, dp, everything. So the trim material should be at least same or higher than that of the piping valves, at least that case. And on trims we will go in depth hopefully in coming sessions, but definitely that material selection is very very critical. Third thing important for you is, when it comes to high temperature, is if you select dissimilar metals, if the trim is of a different material than that of your plug or your stem, each component has its coefficient of expansion due to heat. If they have dissimilar at very high temperatures, I'm talking about something like 600 degree, 800 degrees, something of that level. There are certain applications which require such high temperatures. There you have to be very cautious of if you are selecting dissimilar metals. I would recommend have the same material, because the reason being is both of them, if there are dissimilar metals at such high temperatures, you can have extra stress which can cause the stem to break, or some other issues can happen in the plant. Okay, that being said, if you have any questions related to materials, you want to put them in the chat, you can put, and maybe I can cover it up. If I'm pipe class is okay, WCB, WCC. Ah, okay, okay. I'll answer this also. Okay, if my pipe class is 600 and material is CS, my valve flange is CS and valve body, can you can I use 316L as class 6? My pipe class is 600, material is CS and my valve. No, no, no. If your pipe class is 600 with your material is carbon steel, and if you use a valve body with SS316 as class 600, mostly it is going to fail. Uh, there's a standard called as ASME B 16.34 for especially for valve standards, which we will cover, which has pressure temperature rating. You need to check. Definitely it is not going to, definitely it is, most probably it is not going to work. You might have to go higher, because 316L means the carbon content is even lower, so it is even less hard. So it is getting less hard, so it is very difficult for it to compete with carbon steel. So you need to once look for that. Okay, okay, packing material. Okay. Can we get PDF file? Yeah, definitely you can get the PDF file. No issue with that. Of the presentation. Okay, okay, okay. Good point. Okay. Now, okay, and also, okay, NACE is also a point which definitely. Okay, okay, okay. Till what size can be used forged? Okay. Now this depends on the vendor. You cannot we cannot only say it, but I would say maybe usual vendors around, okay, vendors don't quote me, I'm not very sure, but maybe around 2-3 inches, I'm not sure. Usually they quote, I think above that they usually go for a cast resin, but it depends. Okay, uh, but this can be easily known from the vendor. Okay, should we go for higher material if velocity is high at inlet and outlet? Okay, 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 makes sense. Okay, 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 few points. Now, okay, when to use stellated trim? Okay, a lot of your points are related to which comes to sizing. I think we should definitely cover a separate session in depth on sizing. The reason is, when it gets to the velocities which you said, when to take stellated trim, and this gets a bit depth when you do sizing. Without that, it is a little bit difficult for us to answer. A lot of people assume that okay, when you've done stellated, it is good enough. But personally, no, it depends on how much is the DP that you are having. So that would be this thing. We would recommend velocity at inlet and outlet is high. Should we go for higher grade material? Okay. When to go for hard faced trim? Okay. Flange rating is applicable for valve body also. Yes. Okay. 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 Good points. Okay. So, okay, we'll try to answer slow one by one. First thing is in terms of NACE. NACE is when you have source service. So, for example, whenever you have any source service applications, you go for NACE. You have MR0175 and 0103. The 75 is usually when you have it something in upstream. If it's refineries, you have 0103. So basically in NACE is basically for whatever grades you have. But if you have an offshore application and the vendor gives you, for example, 0103, don't accept it, overall speaking. Okay, the other way around could be accepted depending on what type. If it's painting, yes, you can accept, but if it's exactly the material, I would say no, don't interchange them, because for refinery, sulfide stress cracking is something more severe for them. So 0103 addresses that for depth. So for source service, I would say yes, definitely go for NACE. Your pipe spec will also specify mostly NACE, so from there also you get a clue that okay fine, it's a source service, I need to specify NACE. Soft packing material. Okay, now packing material is something which is a little bit more trickier than this. I'll just give you thumb rules right now so that we are not running short of, because we're running short of time. See, for packing material, you need to see the fluid also. At the same time, temperature becomes very important. And third is, which Mayank mentioned, fugitive emissions. Material, because if that fluid comes out from the packing is also a big issue for you. So these things come into picture. Generally speaking, if your application is an average application, low temperature, if you read APA RP 551 also, it says that go for PTFE, good one. Overall, a all-rounder material for packing, not a extremely tricky application, not very high temperature, go for PTFE. Goes very higher temperature, then depends. I'll try to make, if possible, in this PDF I'll give you a guide kind of stuff where you have basically like, do you require fugitive emissions there? If yes, then you, which packing material you can use. Like graphite for example is good, but then it becomes tougher to contain those emissions. And in fugitive emissions also you have A, B, C classes. So depending on how stringent is your fugitive emission criteria, you need to go for it. But overall speaking, packing wise, low temperatures 200 degree, 250-degree go for PTFE, goes higher temperature 400-degree, so go for graphite. If you have fugitive emissions, you usually start with, first is V-type design, live loading design. If not possible, only then you start to go for bellows and those higher amount of packing. So based on your fugitive emission class, you can then go forward. Okay. Okay, that was one point which I saw had to be answered. Okay, inlet outlet we should do it in the next session. Can you explain practical example how you work from zero for valve sizing? Okay, this can be done. Okay, with practical example from zero to how do you do valve sizing and all selections. Okay, okay. Yes, bellow seal valve will then come in the. It is the worst case scenario. If nothing works, your fugitive emission is extremely high, which is class A, then only you should think for a bellow seal valve, okay? Because it has a lot of maintenance issues, cost is increasing, DP has to be less, a lot of things come into picture. Can you explain the term live loading or how? Okay, we will cover this in the coming sessions. Okay, 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 okay. That being said, uh, since we should, I'll just quickly wind up with just giving you at least the basic international standards. These are not all. If possible, I'll try to share maybe in Excel or maybe a list of all the standards, all the important ones. But here I'm just sharing is which are at least basic and crucial required. First is the valve C2C distances. Okay, here remember that ASME B 16.10 is one very important standard that your valve manufacturer should usually follow. The reason is piping will not wait for your valves to get manufactured. So they will have certain distance that they need to keep between two pipes. Why am I sharing this is in few of my experiences I have learned is, especially if you are giving your basically offers, or basically you are inviting newer vendors who have come into the field, they sometimes don't comply with this face to face dimensions, and at the site it will be a big hassle for you if you cannot match in between the two piping flanges. So first thing is, if you have a new vendor, if it's a reputed established vendor, they usually follow ASPE B 16.10, or there's also an ISA standard which gives you the face to face dimensions. I can't go in depth right now, but when it gets to your RTJ and those designs, when the flange, there you have to be a little bit more, you need to calculate it exactly. If it's a new vendor, that is he complying with the face to face requirements or whatever is mentioned in your project. Second thing, if your valves are special, okay, I don't know if you've experienced this, but if there is some modification or it's a special kind of valve, then sometimes it will not comply with this face to face dimensions. So upfront you need to take the dimensions from the vendor and give it to your piping department, or else later you will suffer when when the valve is manufactured. So this interface has to be very well known. Next, after that is going to be your flange standards. This is ASME B 16.34. If you look in the standard ASME B 16.34, it has various classes: standard class, special class. Usually 99.9% of your projects will be going with the standard class. Check the PT rating based on your standard classes. As somebody said, if your pipe material was carbon steel and your valve is 316L, So probably it might not have the same rating, so your rating will increase, and similarly the pipe rating has to be increased to match the valve with the pipe. Okay, now this is something which a lot of people get confused with. You also have API valve standards. For example, API 623 for globe valves or API 609 for butterfly valves. The point is, should I follow 16.34 or should you follow the API standard? Is one query which comes in. Overall speaking, if you have API 623 for example, it is more stringent compared to 16.34 overall. So if that is the case, then if you have already specified 16 point, uh, sorry, if you have already specified API 623, then you are at a stringent requirement. So okay, fine, makes sense. If you have specified 16.34 but your client wants it to be an API valve, which is usually for the petroleum and the oil and gas industry, you need to specifically mention to the vendor that you need a valve which is manufactured as per the API standard as well. It will not be covered under ASME. For example, the stem thicknesses for a globe valve is higher, so that is how those things have to be definitely taken into care. Third is, which a lot of you mentioned, is the leakage class. Leakage class, I told you one important point. The leakage class mentioned is based on standard conditions. If your valve requires extremely high amount of tight shutoff, do not rely on control valve. Husky accident happened. Even the ExxonMobil accidents have happened a lot, where the control valve could not actually close because. And if you also read the API RP 553, which is also what we'll mention soon, in that also it is mentioned especially for FCC units. This is a very common mistake that used to happen. Please avoid that. Third is your fugitive emission standards, ISO 15848, TALFT. Okay, here something for you to know is in ISO 15848 you have dash 1 and dash 2. So so basically one is where you do an actual testing of all the valves. Certain things where you have just type testing, so you basically test a particular valve and that is basically suitable for all the other valves. Taluft is basically very yet well known. It is usually used in German projects, etc. um, the point here which I would want to make is, when you specify ISO 15848, this standard itself is further divided in the sense, if you read the standard, it has three classes: A, B, C. A lot of the times engineers just mention the standard, and you should check in your specs, do they want a specific testing? Do you want it to be AH class or AB or BH class or C class? So H stands for whatever is the thing. If you're using helium, for example, whatever is the test gas that you use, so basically you have ABC. So if you don't mention, my understanding is vendors would consider C, which is the least stringent, which makes sense. If you have not mentioned, they will consider C. And if you wanted A and you say later, then it will be a big confusion, because this testing is not very cheap. It is a good process, and if all the valves have to be tested, if you go for that, then that is not easy. That being the case, be very cautious when you mention these standards. Second thing is the valve testing, and I wanted to cover calculations, but I was assuming we'll run short of time. So basically here I'll just mention is ISA 75, which has further divided into like cavitation and cavitation index, and all of those things will come here. And for control valve noise, 3 and 4, I think 3 stands for gas and 4 stands for liquid. So the noise calculations have to be done. This is just an overall overview which I'm giving, and then you have is your API RP 553. I definitely recommend you to read API RP 553. You will learn the recommendations for fluid cracker FCC units, etc., what you should do in those cases. So this is just an overview. I'll try to add up more standards also as we go, and then share with you the presentation plus that. Okay, last is, whatever are your questions, we'll put that in the chat. I'll definitely try to answer. And what next do you want that you think would be valuable from my side to you? So I'm waiting in the comments. We'll wait for 5 minutes, and then we'll try to close. uh, I'm whatever, if I've made some mistakes while speaking, please forgive me. And thank you so much for your patience to listen. I'll definitely try my best to answer and try for a part 2 session. Okay, okay, I see. Can you share calculations in advance? Okay, I would share is, I've tried to teach control valves to a few engineers, like a few people from Shell or Exxon. What I was learning while teaching them was, you don't learn calculations by just I'll giving it to you. I see you learn it better when, we have a workshop kind of session where basically you yourself use the software, size it, and come with your queries. But still, if you want, okay, I'll at least give you the basic guidelines. Fugitive emission is nothing but company's new drama. Okay, okay, which is more stringent, ISO or TALAFT? Okay, good point. What has happened right now is with the 2000 and I'm not very sure of the year 2024, I think, or 23, the TALAFT itself has asked to do the testing as per the ISO standard. So based on my understanding, if you have TALAFT, you should be able to and you have the if you have the ISO, it should be at par. But remember the leakage class requirement, that AH or the BH or CH, what is the requirement? So I think it's some 50 ppm, which is very stringent. Okay, so based on that, but overall testing procedure wise, both have now come to the same power. Okay, uh, with software for sizing, I personally prefer is a Fisher control valve sizing because of its personally I see it gives you a lot of errors, like for example cavitation, flashing, choke flow. I've tried a few other softwares also from other vendors and the Instocal and those kind of stuff, but I personally felt Fisher has worked for over the years well for me. So I do initial sizing in the Fisher software. Oh wow, okay, explain how controller works with high pressure lines with only giving actuator 3 to 15 psig. Okay, very good question, huh? Please share presentation. Thank you so much. Okay, okay. Can you please? Okay. Thank you so much. Indicative equal are applicable for, okay, differences between, okay. Yes, the software is free. Fisher specification is free. That is another good point. So you can easily practice. Yes. Thank you so much. I really appreciate you taking the time and for all your support. Thank you so much. We'll be ending the session. Okay. Yes. Thank you so much. End stream.